Alright, so I'm doing some more experiments, some more testing. And I found this proof of concept type of bucking coil test schematic that Chris has shown, just so that you can experiment and see some of the effects, which I believe I'm seeing, where you have a post input which goes from the positive here through one of the coils, through the collector to the ground. That's our pulsing coil, our pulsing PWM right there. And then we have two diodes. Now I've switched out the diodes for LEDs because I like to watch what's happening. But they're acting the same as that. The LEDs are only allowing current to go through one way. So what happens is that gets potentialized, you get your field, this reacts, charging up this cap, and this will react again as a reaction. So you've got action, reaction, and then a reaction to that reaction. So you've got a three-phase. So like he talks about the 1 plus minus 1 plus 1 equals 1. So you always get a little bit more out. So we've got our capacitor, which is that one, our load, which will be our LED there. It's still on slightly, but it's dropping. It's at 11.95 volts. This is our milliamps in. It's on the milliamp setting, as you can see, and we won't really go above 5 milliamps. So yeah, that's the basics of how this circuit should operate, and then you just watch what these coils do and how one supports the other. So technically it will give you more current out than what you are putting in on this pulse here. Now I've got my scope set up as well, so the green trace will be just what is happening with this PWM, so I can check whether everything's correct. And then the yellow is connected to the collector, just so I can see what the collector is doing. Now the whole thing is running off of my 4 volt lithium again, so there's not a lot of energy going through that, and the whole thing is running off of that, off of 25 volts, sorry. Alright, so we've got 3.8 milliamps going in. Our voltage is going up. You can see this LED is starting to light up a bit as the cap's getting charged, which you can also see by the voltage there. Now we're at 10 kilohertz. You can tell and see that on the scope there. Yellow is at 20 volt divisions, and green is on 500 millivolts. You can see there what's happening. Transistor turns on, and then you've got your wave that is doing all our charging and such. And it is saying 10 kilohertz as well, so that's confirmed. Alright, so here's the interesting parts. As usual, if we decrease the duty cycle, we will decrease the amperage, but our charge goes up. And our diode LEDs get brighter. Alright, so we'll decrease the duty cycle again. And now we've got less milliamps going in, and our charge continues getting higher. LEDs are slightly dimmer than before. That's the scope. Still doing exactly the same as what it was doing before. The oscillation seems to be a bit more pronounced though. Okay, so now we will go and increase the frequency. We'll go to 20 kilohertz. LEDs get dimmer. We're at 69.69 milliamps. our charge goes down, as it should. Obviously our LED is getting dimmer, and that's what the scope is doing. Okay, so now we go back to 5% duty cycle. Our charge rate goes up, 2.7 milliamps. 2.27 milliamps. Our LED is getting brighter and brighter. It's a bit hard to tell, although you can tell by the lines. Point source has a very weird effect on cameras. And those LEDs, which are our diodes, are both also lit up there. So we're steady at about 12.7. Now you can push this harder and all that, but there is a point where you get to where if you go too much of a duty cycle, your lights dim, you're using a lot of milliamps, and your charge rate goes down. And you can tell that by also the oscillation. It's not as pronounced. So our resonance isn't there, our charging isn't there, we're wasting a lot of energy. Now the other interesting part is, and the point of me making these pancake coils was to do some E-field testing. So here we have a coil, which is just a normal coil, bought from JCar. Only rewound, mainly so that I can get both ends out. And I've got two LEDs connected to it in an AC configuration, where the negative and positive of both legs are connected, so that if there's an AC signal, both these will light up. And indeed, if we put the LEDs in the middle, you get the LEDs lighting up. So that's nothing new, nothing different, except for when you put them this way, they also light up. Only slightly on, far more pronounced when they're on their axis like this. Now, the other thing that happens is if we go down to our 3% duty cycle, and we take our coil, and if you watch the milliamps, our amperage goes down even more when we use up more energy. Take it off, milliamps go up, put it back on, milliamps go down. So depending on where you get your resonance with these coils, duty cycle, frequency, impedance, all that stuff, once you start matching it up, it has some very interesting effects. Take it off, milliamps go up. Let's go to 4%, 137, and our milliamps drop. And even in this configuration, and that's, not insignificant. It's a proof of concept, and so a way of having a play and figuring out what these bucking coils are actually doing. And as you can see, these are, the red one underneath is wound in a counterclockwise direction, and the top one on the green one on the top is wound in a clockwise configuration. And so they're clockwise and counterclockwise connected together, like here, and then the ends are connected to our diodes. Now I've had to do 3 here and more there. You can play around with the amount of LEDs. The amount of LEDs you put, which changes the charge rate. You can just put normal diodes if you don't care about watching what's happening there, and you just care about this end on the cap. but I like seeing what the diodes are doing as well. If you put too many LEDs here, they won't light, so 3 is about the best. And so that gives you that initial pulse, charge, and then this one supports it again. And it's the only way that these can light and these can light. They will not light if you go this way, because there is no current path. It's all based on the induction. It's based on both these coils interacting back and forth to go back to your load. And how much of a load and what kind of frequencies and duty cycles you get does matter. Now this coil on here, even though it's dropping the you can see there's a slight change in the wave. If I zoom in, and if you watch the wave as I take it off and on, there is a slight change. Very slight. Not much there. But yeah, that's what I'm playing with right now. And that's the documentation for it. Alright, and just to show you what happens if you do get your adjustments wrong. For instance, here we're at 20 kilohertz, 10% duty cycle. We're using 6 milliamps, 6.5. We're at 12.9 volts. That LED is quite bright. That's our signal. And when we take our coil and watch the milliamps, put it over, our milliamps will go up. Voltage isn't affected. Nothing's really affected, but the load on the coils, if it's the wrong load, your milliamps will go up. Comparatively, if I believe I had this at 990 kilohertz. Let's do 80, and we do 20% duty cycle. So our milliamp draw is relatively similar. Same with our voltage. You can see it's bouncing around a little bit. Our waveform is a bit different. And this time, if we take our coil, no, still got it out of the wrong range. All right. See how finicky it is? It must have been dead on 90. Alright, 5.37. Our voltage. There we go. Now we've loaded up the coil, taking extra out. You can see the milliamps have gone down. Take the coil off, milliamps go up. So you have to get your frequencies, your duty cycles, and everything like that spot on. And then you can start getting reductions with more output. Alright. Alright. So I've taken my scope off just so I can verify that there's no funny business happening with ground. And there isn't. As you can see, there are no scopes on here anymore. You will put the coil on, and as you can see, the milliamps drops. Our voltage fluctuates and stays relatively same, which means that capacitor is constantly charged and running that LED this entire time. Now the other thing is ground. This is a ground. This is not a mains ground. As you can see, ground and hot are together here. Basically a short circuit. This would be blowing my mains. This is a ground that's a stake outside. It's relatively deep. And if you take the ground and connect it, it too will give you a net benefit. Again, our input has gone down, whereas our output is pretty much the same. We're still running at 90.1 kilohertz, 20% duty cycle. So as you see in some of the videos of the Pancake and Akula and all those Russians that have been building all those years ago, along with Floyd Sweet and all those other inventors, where they always have ground. And the ground is one of the keys. You have to get a good ground, not mains ground. It has to be a proper ground. And it inputs into the system. You basically have got an electron sink right there that adds to your entire system. And just to show that there's no funny business, what we can do is we'll disconnect the battery and you can see the whole system run down. So this capacitor is now running down. So is this one. This one's just across our battery, our positive, which is here. And our LED is running down. Now we're no longer getting the field, any of that good stuff. And then if we connect it back up, we start getting our charge. And you know that this capacitor is not being charged by this one or the battery, because if I switch it over to 25 volts, 24 volts, that capacitor only goes up to about 13 volts at 9 milliamps. Although if I disconnected the load, I'm sure it would shoot up to maybe 100 volts. Actually, I wonder if that's, let's see. So as our voltage goes up, our input will go down. Now it's reached equilibrium, and now the frequency has changed again, and we're going down again in milliamps, yet we're still pumping more charge into the cap. And this should go through a couple of different cycles as it charges this cap. Although at these lower voltages and things like that, it's probably not going to happen as many times. So yeah, it's going to take a while. So we'll probably charge, yeah, probably hit 100 if our input was a bit higher. Frequency for this is probably a bit too high at the moment. But yeah, just wanted to show that, yeah, it's hooked up exactly the way it's there. So yeah, you can have a look at the whole setup there. Pause, zoom in, check all the leads. It's all as said. Voltage goes up, milliamps go down. What a strange little beast. And also to show that the whole thing is being run by those batteries through that transistor, which is here, and being run by this PWM circuit. We can just turn off the PWM circuit and you can see our input drops instantly. Our voltage will stay because that cap will hold it for a while. So that's 42 volts, 43. So I'm gonna wait overnight, go to sleep now, and watch that bleed off, because I ain't touching it.